Good day, my name is Alexander,
I am Surya.
and today we're going to present on image generation improvements and why they're useful.
So, a little bit of background, our topic is image generation models, and some of their uses are improving image recognition models such as face and thumbprint recognition and virtual reality. And we're going to be comparing the results of our program with the results of our autoencoder homework 4 because we think that that is a good comparison. More specifics about GANs and how GANs work. So GANs are two neural networks. One is the generator, one is the discriminator, and they're competing against each other. So the generator's goal is given a noise data set, produce images that the discriminator will identify as real. The generator will be penalized if its generated image is identified as fake, and the discriminator is penalized if it can't identify a fake image from the generator.
Some things that can go wrong. GANs are very powerful, so they take a long time to train. That's why I implemented progressive GAN. It takes much less time to train, and that's one of the improvements that we made. Secondly, if the discriminator is powerful, the generator will not learn anything because the derivatives will be zero. And sometimes generator will overfit to the discriminator and will output only one image without any diversity. And that's where the problem we'll also address in our presentation.
Okay, so the added improvements that we made, the first one, progressive overloading. So we start off with very, very small convolution layers. Example, in our image, we start off with a 4x4 layer in our generator and discriminator. And as we go along in our program, we will make these layers progressively larger. We can see from the left image that the image is very blurry. We can't really identify a face. However, once we add a second layer, the 8x8, we can start to see that the image becomes less blurry and we can see the face better. And we're going to keep going until we have some significantly large layers. For example, 120 by 120, or in this case, they have 1024 by 1024. And the second improvement is mini batch discrimination. So we're going to have the discriminator analyze images in batches instead of looking at each image separately. And this prevents the generator from outputting the same or similar images.
So we're going to show the code a little. That's how our model looks like. We have the discriminator and the generator. We also have the pixel normalization after each convolutional layer and some custom convolution layers. We also have average pooling and upscaling for the scaling of our models that I'll explain later. Each model has has two RGB and from RGB layers. Basically, each image that goes into generator and into discriminator goes to these layers. So the RGB is here and from RGB is here. And each both generator and discriminator have add module function that basically adds more layers. And the foreign function includes the scaling thing. So when we add layers, we don't shock the already trained layers. So we get like 1% of the output of the second layer if you add it, and like 99% upscale to the output of the previous already trained layer. And we also have mini batch discrimination implementation, which basically calculates the statistics over the batches and adds one more neuron to the discriminator. So, for example, the generator produces the same images over and over again without any diversity. The statistics will tell the discriminator that all the images is fake, so the generator will learn to produce as diverse images as he can. And the main ProGAN model has also the gradient penalty. So generator will not also overfit the discriminator. This added to the training loop, which includes the scaling and adds layers as we go. Yep.
Okay, so the results from homework 4, this is our reconstructed data and our output. And we can see that while we are generating faces, they're not very good quality and they're not very diverse. So we can't really do anything with these. However, for the GAN, we can see that, okay, when we have small resolution images and small layers, our images are blurry. We can't really tell the faces. However, once we increase our layer sizes, we increase the resolution and we take into account the results from previous layers and the results from the current layer, we'll see that images become a lot clearer, a lot more diverse, and different backgrounds too.
That means that our mini-batch discrimination works, and gradient penalty allows the generator to generate images that are in the domain of the discriminator, which also improves the generation. These images were trained for 3 days, and they're already good enough, so you can recognize the faces. Like each face have different skin colors, different hairstyle, and so on. So to prove that it works, we use the inception score. We also created the mean and standard deviation for each of the size of the image, for each of the stage of the model. And for this model, we used Inception v3, um, already pre-trained, which has 1,000 different classes to look at. And this is the graph for each resolution. So it's 4x4, 8x8, and so on. And the value for the mean and standard deviation. And we see the standard deviation is very low, which means that our generator consistently keeps producing very diverse images. And mean is from 1.5 to 3, which means that our generator produces several classes, which is really good because faces are in general like only one class, like faces are faces. But that means that it produces like very, very diverse faces, which makes the inception score go higher. Uh, and I think that's it. Thank you for listening.